So here's the dreaded second question. We've got a rocket with a total mass of 20 kilograms. 8 kilograms is the rocket, which means it's carrying 12 kilograms of fuel. Holy subtraction problem, Batman. Right? It consumes the fuel in 4.7 seconds. And at 4.7 seconds, it's got, at the instant it's burning that last little bit of fuel, 8 kilograms of rocket still, 0 kilograms of fuel. So here we got a total mass of 8 kilograms, right? And the first thing says, what's the mass of the fuel? What's the burn rate? Okay? So A, the fuel mass is just 20 minus 8, 12 kilograms, right? And then the fuel burn rate is 12 over 4.7. Right, so this is kilograms, this is seconds, right? So it's just the fuel burn rate is kilograms divided by seconds. So 12 divided by, this is 2.5532 kilograms per second. Did I get it right? Yes, I did. I'm doing pretty good here. Okay. And then B says, what's the velocity of the exhaust gases leaving the engine?
So wouldn't it be 1290 times?
Yeah, there's lots of ways you can do this, okay? My favorite way is just say force times time is mass change in velocity, right? Right, and so I'm just going to do it this way. I'm going to go 4.7 equals 12 kilograms burned, delta V we don't know, right? And this is 1290, isn't it?
Yes.
Right? So you could do it that way. So I'm going to do it that way. I'm going to store this guy. And then I'm going to go to 1290 times 4.7 divided by 12. And it's 505 point delta V is... Okay. The other way to do it is that the thrust of the rocket engine is the burn rate times delta V, right? So that's going to equal 2.5532 per second times your delta V, and that equals 1290. Right? This is the force, this is the burn rate, that's the delta V. So 1290 divided by my burn rate, which is this guy, right, gets the same exact number. I get 505.25. This is my favorite way to do it because why not, right? And then C says, what are the initial and final accelerations of the rocket? Don't forget gravity. Oh, good God. Okay, so C, I was looking at the next question. It's like, wow. Okay, so the initial acceleration, this is one of the forces, but is that the only force acting on it? Do you suppose there's a force of 1,900 and, wait, I don't know, it's 20 kilograms, right? The force down is going to be, right, so 20 times 9.8 is 196. There we go. Right? So for this one, I'm going to do this. The initial is going to be 1290 minus 196. So this is the force up, that's the force down. Right? Equals 20 times A. So 1290 minus 196 divided by 20, 54.7. Yeah? Did I get that one right? Yes, I did. At the end, okay, it's still 1290 of thrust, right? On this rocket, there's still 1290 up. But now the force down is just the weight of 8 kilograms, right? So 8 times 9.8, right, is what? 78.4. Right, so it's much less weight. The thrust is still the same, but this guy is down. 78.4, that being the weight of the rocket. And so it's more for two reasons. One, there's less weight, and the other is less mass to accelerate, right? So it's going to be 1290 minus. And this was actually a problem when they did the moon launches. The rocket had so much thrust that when it was just about to run out of fuel, the G-force would have been too high. So partway through the burn, they actually shut off one or two of the engines. I can't remember, but to prevent the G-forces we're about to calculate, right? Okay, divided by 8. And when I do this, I get 151.45. Neither one of these would be that terribly suitable for astronauts, but, you know, if this was barely our limit, 3 times that would be. Did I get that one right? It's always good. He rounded that one up. I think it's 151, but that's okay. And then D says, if the rocket burned the same fuel in the same time, in other words, this number is the same, okay, but the exhaust velocity changed to 1778 meters per second, what is the thrust force of the engine? Well, I think we've got to use this formula here, right? Okay, so D, we're going to say the force is the burn rate times the exhaust velocity. The burn rate is this guy, so I'm going to go 2.5532. So it's the same mass in the same time, right? And then the exhaust velocity is 1778. So let's see. Do I still have that number? I do. Times 1778. And I get that this equals 4539.57. And the answer here is 4534. I'm going to argue that I'm right, but really it doesn't matter. We're arguing about a digit that's not even that. The other way to do this, guy, is this. I'll put it up here. Okay? You can do the same mass in the same time. So F times 4.7 equals 12 times 1778, right? And this gives exactly the same thing. And that's all we got time for, kids. See ya.
It might just be archived.